This is Chemistry Unit 6, Chemical Composition, Molar Mass. One atom of aluminum has a mass of 4.48 times 10 to the minus 23rd grams, which is a really small number. Now this mass is determined by adding up the masses of the protons, neutrons, and electrons within the aluminum atom. So knowing this, what would be the mass of 1 mole of aluminum atoms, or 6.02 times 10 to the 23 atoms of aluminum? Well, we can set this up using dimensional analysis. So we're trying to find the mass of 1 mole of aluminum. So that's your starting point, 1 mole of aluminum. Now you've already learned this conversion factor of 1 mole equaling 6.02 times 10 to the 23rd atoms. So just be careful on where you place your factors. The 1 mole needs to be on the bottom so that it cancels with the original mole. So moles cancel and you are left with atoms. But you were not asked to determine atoms. You were asked to determine grams. So you do have a conversion factor between 1 atom and grams. It's right up here in this first statement. In 1 atom of aluminum, you have 4.48 times 10 to the minus 23rd grams. So just be careful where you place your factors. 1 atom is on the bottom so that it cancels with these atoms and you're left with grams. Now to solve this in your calculator, you will take 1 and as you go across you multiply, and you multiply that by 6.02, the EE key, and then 23, and then times it by 4.48, the EE key to the negative 23. Now on the bottom, it is 1 times 1, which is just 1. So if you want to type in divided by 1, you can, but you will still get the same answer. And my answer is 26.97 grams. Now I know I did not follow significant figures here, but there's a reason, and you'll see that in just a second. So this 26.97 grams is the mass of 6.02 times 10 to the 23rd atoms of aluminum, or 1 mole of aluminum. Now, what I'd like you to notice is where you might actually see this number. If you look on the periodic table at the box for aluminum, look at that decimal, 26.982. We learned that as the average atomic mass, right, for aluminum. But now what that's also representing is the mass of 1 mole, or 6.02 times 10 to the 23rd atoms of aluminum. So this number has another meaning. So therefore, 26.97 grams is the mass of 1 mole of aluminum, or 26.97 grams per mole. So more commonly stated, 26.97 grams per mole is the molar mass of aluminum. The atomic weights of the elements on the periodic table also represent the molar masses of every element. Now, just a quick reference to my significant figures. So you can see that sometimes these average atomic masses have 2 decimal places. Sometimes they have 3 decimal places, right? Sometimes they have 4 decimal places. So usually I follow 2 decimal places when looking up these molar masses. So that's why for my answer, it was 26.97, and I didn't necessarily follow significant figures because I knew that was also referencing the molar mass. So let's find the molar masses of some atoms. So this really just means looking on your periodic table. So my first example is magnesium, which is right here. So I usually round that to 24.31, but notice my units, gram per mole. Okay, how about the molar mass of tungsten? Tungsten is the W on the periodic table. So that already has 2 decimal places, so I leave it as 183.84 grams per mole. And now how about oxygen? So here's oxygen, 15.999, but careful, if I just say oxygen, it's diatomic, so it's technically 32.00 gram per mole. Okay, but that's only if oxygen is alone. Now, how can we determine the molar mass of a compound and not just a single element? Well, you must know the chemical formula of the compound. So for example, sulfur trioxide's formula is, do you know it before I reveal it? This is molecular, this is type 3, there's no charges, there's no polyatomics. You just write what the formula tells you. Sulfur would be S, the tri is 3, and oxide is O. So this is SO3. Now, step 2, you will add the molar masses of the individual atoms in the molecule. So the mass of sulfur, you just look it up, 32.06, already 2 decimal places, so I'll just leave it. And now oxygen, remember oxygen, we round the 15.999 to 16. Why is this not 32? Because this is not oxygen alone. Oxygen is part of a formula, so or a compound, so you use however many oxygens are in that formula. So this is 16.00 times 3, which is 48.00. And then you add them up and be sure to give the proper units. This is 80.06 grams per mole. So this is the molar mass of a compound, not just a single element. So let's try one more. How about ammonium phosphate? So now you have to refresh your polyatomics. So you have a polyatomic chart, because none of this is on the periodic table. There's no ammonium element or phosphate element. So here they are. This is ammonium, NH4 plus 1, and phosphate, PO4 minus 3. These are both polyatomics. So now you have the charges. Now you need to exchange them. So the proper formula is NH4 in parentheses with that 3 on the outside. Otherwise, it's NH43, which is just not right. And then PO4. And now when you try to find the molar mass, I go element by element. And you have to be careful to remember if they're in a parentheses with a number on the outside, you need to distribute. So let's look at nitrogen. I just go left to right. So nitrogen, if you look up its mass in the periodic table, 14.007. I usually say 14.01. Why am I timesing it by 3? Because it's in a parentheses with this 3 on the outside, and that 3 distributes. So 42.03. Hydrogen. If you look up hydrogen on the periodic table, it's 1.008. So I will round that to 1.01. Why am I multiplying by 12? You have 4 hydrogens within the parentheses times 3 on the outside. 4 times 3 is 12. So 1.01 times 12 is 12.12. Now phosphorus, it's not in a parentheses. This 4 or this 3 are not next to phosphorus. So you just look it up. 30.974. I round that to 30.97. And then oxygen, we usually round the 15.999 to 16. There's 4 in the formula, so 16 times 4 is 64.00. Add them up, and your molar mass is 149.12 grams per mole.